Howdy and welcome back. Today is session 4 and we're going to talk about drag. If you remember last time, we talked about how the rate of change of momentum on the flow affected all the forces, and the rate of change of the vertical momentum affected the lift. And today we're going to talk about how the rate of change of horizontal momentum is related to the drag.
Remember how the original momentum of an air ball was altered by the wing to some new vertical momentum, which is related to the lift? At that time, I said the horizontal momentum decreased in the process. That change in horizontal momentum is related to the drag, and that's the emphasis for today's discussion. Now, since the wing forces the flow to slow down, then Newton's third law says the flow forces the wing back in the drag direction. If I want to push an object through the air, then I have to continually force this change in the horizontal momentum. Recall, the equal and opposite force to drag is thrust, which must come from the engines.
Of course, an airplane with a lot of drag needs a big engine, and that means a lot of fuel and a lot of money. The trick to designing an efficient airplane is to make one that's low drag, and that's one that changes the horizontal momentum as little as possible. Now, if you look at the drag equation, what you'll see is drag is equal to the mass times the change in horizontal velocity divided by the change in time. So you'd like to change the horizontal velocity as little as possible and do it as slowly as possible. That should sound familiar because we had a very similar equation for lift.
Making something high drag is easy. To do that, just change the momentum abruptly, like putting a flat plate perpendicular to the flow. From the simple discussion, you would think that streamlining is the key and that nobody would build a blunt moving object.
Having said all that about flat plates, you would think a designer would try to streamline objects that move through the air. Taking a look at this motorhome, however, you see that it's a little bit on the blunt side. Well, they have reasons for doing that. Sometimes it's for structural strength or to maximize the internal volume or whatever. Now, you can get away with that on a motorhome because it only goes about 50 or 60 miles an hour. On an airplane, however, that goes 200, 250 miles an hour, that's an awful lot of drag, and a designer would never do something like that.
Suppose instead of a flat plate, we use a more rounded shape like the cylinder. The flow still loses some of its horizontal momentum, but not quite as much or as abruptly. Since there's less rate of change in momentum, there's less drag.
If reshaping helps a little, what happens if we reshape the object a lot?
Here, we see that there is a very small change in horizontal momentum. Recall that another factor that affects the momentum change is the angle of attack. Tilting an airfoil makes the shape look more and more like a flat plate, which we already know has a lot of drag.
To calculate the amount of drag, we use a term called the drag coefficient, which we abbreviate as CD. Now, that's just a measure of the effectiveness of the object at creating a drag force. To actually measure the drag itself in terms of pounds, all we have to do is multiply the CD times 1/2 times the density times velocity squared times the area. That might sound a little bit familiar because there's a very similar equation used for describing the amount of lift, except instead of CD, we use CL. To demonstrate the velocity squared effect, we've rigged up this simple experiment. We have a flat plate on the end of a pole that pivots, and to hold this flat plate in place, we have a cable. As we drive down the road, we're going to have the air forcing that flat plate back, and we're going to measure that drag force with this spring scale that's calibrated in pounds. Okay, go to 10 miles an hour. Now, the theory says that as the velocity increases, the drag will go up with the square of velocity. Let's see what we get. Okay, at 10 miles an hour, I'm getting basically 1 pound of drag force. Okay, go to 20. Now, if we double the speed, we should quadruple the drag force. When we get stable at 20 miles an hour, we'll take another reading. Okay, that's about 3.5, 3.5. Okay, go to 40. So we're going to double it again, so we should quadruple that last drag force, or 60 times the original. So at 40 miles an hour, we're reading 15.5 pounds of drag. Okay, if we were to plot up on a piece of graph paper the drag force versus the velocity, we should see something of a square effect. What we say is that the drag is linearly proportional to the square of the velocity. For the experiment we just did, we had a constant air density, object size and shape, and angle of attack. Now we can repeat this entire series of tests at the same airspeed and change only the angle of attack to larger and larger degrees, and then we can plot the drag versus the angle of attack. We can also do the same series of experiments by changing the shape of the object. But I know a much more interesting way. When you were a kid riding your bicycle down a hill, you could just coast, let gravity do its thing, let the weight of the bike pull you downhill. You could do the same thing on a sled or on skis. Well, we could do the same thing in an airplane. Now this glider here doesn't even have an engine. So if the pilot wants to fly at a constant airspeed, all he has to do is point downhill and off he goes. Now if we make the glider streamlined, then it can go down at a certain airspeed with less vertical velocity. It can have a longer glide range. So by cleaning it up, minimizing the aerodynamic drag, we can have a good, efficient glider.
The airplane has some drag force, D. Since we don't have an engine to provide the thrust force, we have to use the aircraft's weight, W. To illustrate this, recall from previous discussions that the weight is centered at the CG and its force goes towards the center of the Earth. The weight force can be broken down into two components, one perpendicular to the drag axis and one parallel to it. If we tilt the airplane nose down just enough, then this parallel component can just equal the drag. From trigonometry, we calculate this thrust force as the weight times the descent rate divided by the true velocity. To fly at a constant airspeed, the thrust force must be equal to and opposite of the drag. Let's calculate the drag of our glider at a speed of 50 knots.
After being released from the tow plane, gliding back towards Earth now at exactly 50 knots. The weight of the aircraft is 1,051 pounds. Now I'm going to use my stopwatch and the aircraft's altimeter to time my altitude loss, calculate my sink rate back to the Earth. Stop my watch. 1 now. Now because it's a glider, it has pretty low drag. So it takes a long time to descend. Coming up on my first 100 feet in about 10 seconds. There's my first 100 feet. I'm going to go another 100 feet just to make sure I have good data. Got about 20 feet to go. Air's nice and smooth up here. And here we go. Ready, back. Okay, we dropped 200 feet in 55 seconds. So that essentially establishes our descent rate. This glider is streamlined so well that the drag is very low. It's so low, in fact, that the pilot sometimes has difficulty in doing a pinpoint landing, because as he tries to land in just the right spot, the airplane has too much lift, not enough drag, and it just keeps wanting to fly. So to solve that problem, what the designers have done is install these speed brakes. And what they do is act like flat plates that abruptly change the momentum of the air. You can see that there's a speed brake on the upper surface and the lower surface. Now each one is about 4 feet long, and you can see that compared to the size of the overall airplane, it's a pretty small percentage. How much drag do you think they add? Another 10% drag? 20%? 50%? Well, let's go out and fly again with the speed brakes open and see what happens. Okay, here we are again. Same conditions, same airspeed, and the same weight of the aircraft. And this time we're going to make one change and extend the speed brakes. Now, in order to keep the same airspeed on the airplane, I'm going to have to point the nose down a little bit steeper and use more of that gravity to fight off the drag of those spoilers. I'm going to start timing in about 5 seconds. Ready? Start. Sink rate is much quicker. There is 100 feet now. I'm going to go to 200 feet and stop the watch at 200 feet. Ready? Ready? Back. So that was 14 seconds to descend 200 feet, whereas last time it was 55 seconds. What sort of a percent change is that? It's almost 4 times. But basically, we have almost 4 times the drag. It breaks down. Who would have thought that such small surfaces could have made such a large difference in the performance of the airplane? It's not that they created such a large drag force, it's just that the airplane was so streamlined without them that a small change makes a large difference in the performance.
Back in the old days, aircraft designers had a feel for the drag generated by different shapes, but they ran into problems as they tried to streamline airplanes. They had problems such as structures which weren't strong enough, or because the engines didn't have sufficient cooling, or several other things. Today we know a lot more about solving these problems. We know more precisely what shapes give the best drag. That's why modern airplanes look so cool, because they are.
And speaking of drag, looks like they're about ready to drag me out of here, so until next time, this is Danger Al saying, adios! Help! Slow down! You scared me! Stop it! What are these little footy things doing?